guys, today we're going to talk about the mathematical expression of delta G. But before that, let us review what G, H, and S are and what they mean in terms of their signs. So let's go ahead and identify H, which is enthalpy. So enthalpy, by definition, is the name given to the amount of heat evolved or absorbed in a reaction at constant pressure. So if delta H is negative, it is an exothermic reaction, meaning it would release heat, causing the temperature of the immediate surroundings to rise. And if it's positive, then it would be an endothermic reaction, where it would absorb heat and cools the surroundings. Moving on to delta S, we have entropy. And entropy is the dispersal of matter, and the value of S would increase when a solution is formed, volume is increased in a gaseous system, or when complete molecules are formed. So delta S would be negative if the system is becoming more ordered or less dispersed, and if it's positive, then the system is less ordered or more dispersed. And usually in problems, delta S is given to you in joules per Kelvin. Keep that in mind. And for delta G, we have Gibbs free energy. And Gibbs free energy measures the thermodynamic favorability or spontaneity of a reaction. It is thermodynamically favored when delta G is negative, meaning it would be a spontaneous reaction, and it would be thermodynamically unfavored when it is positive, meaning it would be a non-spontaneous reaction. To give you a deeper understanding of this whole thing, I have a chart, and for the first one, this shows a spontaneous reaction in which delta H is negative, delta S is positive, and delta G would be negative. It would be a spontaneous reaction, meaning it would be thermodynamically favored. For the second one, it would be the opposite, where delta H is positive, delta S would be negative, and delta G would be positive, meaning it wouldn't be spontaneous at all temperatures. And for these two, so if both delta H and delta S are positive, then it would only be spontaneous at high temperatures, and it wouldn't be spontaneous at low temperatures. And for the last one, if delta H is negative as well as delta S, then it would be favorable at low temperatures and not at high temperatures. So I have here a problem, and delta H and delta S is given to you as well as temperature. And looking at the values of delta H and delta S, they're both negative and the temperature is pretty low, so you can assume that delta G is negative. But if you want to look for the actual value of G or delta G, you can just plug these into the equation. But first, look at the signs, see if they're the same. Well, in this case, it's not, so you have to convert one of them. So for me, I converted delta S into kilojoules, so I had negative 0.15 kilojoules. So now that I have converted my delta S, I could just go ahead and plug them into the equation. So I have negative 120 kilojoules minus the temperature, which is 290 Kelvin, times negative 0.15 kilojoules, and then I ended up getting negative 77 kilojoules, and it is negative at low temperatures, since we're given a low temperature and negative values of delta H and delta S. Moving on to a different problem, I have here carried out at 25 degrees Celsius in 1 atmosphere, calculate delta H, delta S, and delta G using the following data, which is the one below. So you have all these H and S values. You just have to look for delta H and delta S first before solving for delta G. So for delta H and delta S, you have the equation, generic equation where you have the products minus reactants. So for delta H, we're looking at the chemical equation given to you. You have 2 moles of the products, and the H value is negative 396, so you have 2 moles of that, as well as the reactants, which is 2SO2, and in 2SO2 you have negative 297, and for O2 it's just 0, so you just disregard. And so when you calculate it, you end up getting negative 198 kilojoules per mole. And for delta S, it's the same thing, and I end up getting 0.187 kilojoules. And before I even solved for delta S, I already converted the values of delta S, because in the chart it's given to you in joules, and before I solved for it, I already converted it to kilojoules, but you could always convert the value into kilojoules after solving for it. It's just the same thing. So now that we have the values of delta H and delta S, we could just go ahead and plug them into the equation. So plugging them in, we have negative 198 kilojoules minus the temperature given, which is 298 Kelvin, times a negative 0.187 kilojoules, and so I ended up getting negative 142 kilojoules. And again, it's negative in low temperatures since delta H and delta S are both negative and we're given a low temperature. So yeah.